Welcome to the physics class for February the 22nd. Before we get started, as usual, we got the administrative announcements. So do not forget about the test rework. It's due this coming Saturday at midnight. If you got 100% or higher, you don't need to do it. I will automatically give you credit for it. And if you're in that category and I forget to give you credit, then just send me an email, a little gentle reminder. I do sometimes mess up. So just if you remind me, I'll fix it. But if you got anything less than 100, including even if you just got 99%, which some of you did, then sorry, but you got to redo all of them. And by the way, the last problem on the test, which was an extra credit problem on the original test, is no longer an extra credit problem. I want everybody to do that last problem. I think there's really good stuff to be learned from doing that last problem. And it's not that hard. Okay, that's all I can think of for administrative stuff. I mean, don't forget about tutoring. Tuesdays, Thursdays, Fridays, Saturdays, lots of opportunity for tutoring. Okay, well, tell you what, let's go ahead and jump right into the physics. Here, I'll share my screen with you. Here are the answers to the questions you haven't already looked up, which is only 2 of them. Now, the first 2 questions in the homework, those are ones that I want to discuss right now. So let's take a minute and talk about it. Let's see, who should I pick on? How about Maya? Could you please unmute yourself and tell us what is one of the 2 reasons that we talked about last time for why it is that scientists were convinced, way back, well, actually it wasn't that long ago, but anyway, why is it that they were convinced that light could not possibly be a wave? There were 2 reasons. Maya, just give me one of them.
Yeah, so waves were when things pass through a medium, and when light comes from the sun, it travels through empty space, and empty space doesn't have anything in it, so it can't be a wave.
That's a pretty convincing argument, I think. Okay, so a wave is by definition a disturbance in the medium. So if empty space really is empty, which is what everybody was sure was the case, then there's no way that a wave could travel from the sun to the earth. So therefore light can't be a wave, must be a particle. All right, but there was another reason. How about, let's see, who have I not picked on for a while? Calvin, I don't think I've picked on you for a while. Can you unmute yourself and tell us what was the other reason?
They believed that the shadows had very distinct and defined edges, but in reality, if you zoom in, it's really kind of like blurred a little bit.
Okay, very good. Yeah, so the people back then, they were very familiar with waves. They knew about water waves and sound waves and all these other waves. And water waves and sound waves diffract, and not just a little, they diffract a lot. So when they looked at the shadows and they saw really sharp edges to the shadows, then they said, well, we shouldn't be seeing sharp edges here. If light waves diffract the way that other waves do, these should be horribly blurry, and not just a little bit blurry, but they should be horribly blurry. If a light wave, if a water wave was to pass by the same size obstacle that the U would be, I mean, if you're standing there casting a shadow, if instead of a light wave there was a sound wave, your shadow would be so blurry that you wouldn't even be able to see it at all. Okay, so I want to take a minute and I want to talk about that. There's something that I wanted to talk about last time, but there just wasn't time. And so I put a video on Canvas that I wanted you guys to look at, and I hope that you did. Let me navigate to the right page here in Canvas. And while we're at it here, maybe what I'll do is I'll share it with you here. Okay, all right, here we go. Okay, so if you go to Canvas and you click on the assignment that was due today, that's this one right here. Okay, so here was the description of the assignment. But if you look down at the bottom here, there were a couple of videos that I put there to help you. This video right here talks about diffraction in a very important way in it. And I want to take the minute to play it now. I think it's worth taking the time now. So let's make it be full screen here. All right, so what you're going to see is a really neat apparatus for creating waves in water. Okay, so this guy right here, he's going to be talking, but I'm going to leave the sound off because I want to do the talking here. He's got a device which I'll show you if my screen will let me. Okay, so this right here is a tank of water. This right here is a special device that moves up and down. So this device here has an arm that makes it move up and down, which makes this entire piece move up and down. And so it's going to send waves out here through the water. In fact, let me play the video a little bit further so you can see. Okay. Hey, there we go. Okay, so you can see it much better now. All right, so what's happening is, so this arm, right, every time I change here, I have to turn off annotation, then I have to turn it back on again. So this arm that you see right here is moving up and down, which causes this whole apparatus move up and down. And so it's making waves, and you can see here the waves are coming out like that. These are what we call plane waves because they're all, you know, nice and parallel to each other. So these plane waves are all coming out like this in the water. Now this thing that you see right here, this is something that blocks the waves here. And the guy is, in just a few seconds here, the guy is going to put some additional blocks right here so that he can make the opening smaller if he wants to. And he does want to. So let's start it playing again. All right, so there's one of the things and there's the other. Okay, so what he's done now is he's made it so that the opening is a lot smaller. And so the only place that the waves can get through is in this central area right here. Now, the important thing is I want you to watch what happens to the waves as they come through this opening. Okay, so let's restart it. Now we're going to switch in just a second to a top-down view. Okay, now we're looking at the top-down view right now. And look at what's happening here. So we've got the waves right here coming through the opening. And then when they come out the other side, you'll see that they spread out. This is diffraction. So what you are seeing is diffraction. Now they don't spread out all the way because over here you don't really see much and over here you don't really see much. They only spread out a certain amount. And what the purpose of this experiment is to find out how much spreading out there is as a function of the size of the opening. So he's going to play with the size of the opening here. And I want you to note how much spreading out takes place. All right, so let me erase some of this. I'm going to keep the yellow marks that are there right now. Let's keep that as a reference. Okay, and then let's replay the videos more. So you see the diffraction that's taking place. Now he's going to change the size of the opening in just a second here. Okay. Come on. Okay, so what he's saying is that I'm going to change the width of the aperture and see what happens. Okay, so now look what he did here. He made the aperture, aperture is another word for opening. So he made the opening smaller. Okay, look at what's happening. You're seeing that the spreading out is more noticeable now. You can see the waves now go all the way out to here and out here. So we're getting more spreading out than we used to get before. So when the opening is small, then you get lots of diffraction. Okay, and now what do we mean by small? Well, when we say small, we're talking about small relative to the wavelength. So if you look at the wavelength here, so from this peak to this peak, that distance right there, that's the wavelength. And so here's the opening. And you can see that the opening, let's call it D, is the opening size. it's approximately equal to the wavelength. Okay, so the rule is that if d is approximately equal to the wavelength, and especially if d is less than the wavelength, okay, then you get lots of diffraction. So write that in your notes, okay? If d is approximately equal to the wavelength, or if d is less than the wavelength, then you get lots of diffraction. Now, what happens if you make the opening bigger? Well, okay, let's see what happens. Okay, in a minute, he's going to make the opening bigger here. Here he goes. Okay. What do you notice now? You got a lot less diffraction. Okay, the waves are pretty much just going right straight through. I mean, there's a little bit of spreading out here, okay? A little bit, but for the most part, they're going right straight through. So if the opening is larger than the wavelength, then you get less diffraction. Okay. All right. So way back in the days that we're talking about here, scientists were very familiar with waves, and so they knew how much diffraction to expect from a wave. And so when they look at the sharp edges of the shadows, you know, some of you say, well, yeah, if you look really, really close, it's a little bit fuzzy. But they were saying you shouldn't have to look close because the waves that they were familiar with had wavelengths that were relatively large. And so with the wavelengths of the size that they were used to, they should have been seeing a lot of diffraction. You should not have sharp edge shadows at all. They should be horribly fuzzy, and they weren't. So the thing that they didn't know is they didn't realize that the wavelength of light is really, really, really small. In the homework last night, some of the problems that you worked with, the book told you what the wavelength was. And did you know what they were? The wavelengths were so small, they were measured in nanometers. A nanometer is 10 to the negative ninth meters. That's 1/1 billionth with a B, 1/1 billionth of a meter. That wavelength of light is astoundingly small. Excuse me. So the scientists back then, it never ever occurred to them that the wavelength of light might be that small. They were expecting that if light was a wave, it would have a wavelength more on the size that they're familiar with. Okay. Had they realized that the wavelength of light was so astoundingly small, then they would not have been so surprised to find that it doesn't diffract very much at all. Sorry. Yeah, I must have swallowed wrong or something. Okay, so now that we know the light is a wave, and we look to see why are these shadows, why do they have sharp edges? Well, we know it's because the wavelength of light is so small, and that's the way diffraction works, is if the wavelength is really small, you're not going to get nearly as much noticeable diffraction. Now, the other reason that we talked about just a minute ago about empty space being empty, that one is a much more interesting problem. Okay, we have proven that light is a wave. So what does that mean about empty space? Well, the inescapable conclusion is that it means that empty space isn't really empty. And we're not talking about the fact that, yeah, there's a few molecules scattered here and there. No. I mean, even if you get rid of those few molecules, if you have an absolutely perfect vacuum with no molecules of any kind in there at all, it's still not empty. There's still a fabric there, which is the medium that carries light. And we're going to study a lot more about that fabric in about a month, maybe a little bit less, but not until after our next test. Okay, with that being said, let's go back to here. Okay, I think we've discussed all the things that I wanted to discuss. So now it's time for you guys to choose. If you could only see one problem worked through, please type into the chat box telling me what that problem would be. And we're only going to have time to do one. So Let's see what you guys want to see. All right, some of you are saying none, which I think is possible because I do think the last night's problems were relatively easy. But if any of you want to see some, speak up now. So far, the only messages I've seen have been none. Okay. All right, looks like none it is. All right, great. Well, that tells me the last night's homework was easy. Be careful about using the small angle approximation. But let's talk about that. Because in last night's homework, you were able to get away with using the small angle approximation, but that is not always going to be the case. So let's talk about it real briefly. Let's just quickly rederive the equation that you used last night. Let's go into a whiteboard here. All right, so the equation that we used last night was, the way we got it was here's our double slit. This is the wall. Okay, this is the distance from the slit to the wall, which we called L. Here's the central bright spot, right in the region that is shadowed by that central blockage there, right in the region where Isaac Newton never would have guessed that you would have seen light. And then way up here is the first diffracted bright spot. All right, and so what we did was we made a triangle right here. Let me make it a little fatter even. So we made this big black triangle here where this was L, this was X, and this was H. And then this here was the theta that we were interested in. And then, let me switch to a different color. We created another triangle by taking a line from here to, let me do this in, make it be thin pen rather than thick pen. Okay, so from here to here, and then from the lower spot up to here, and then we cut it off here. So this was pretty much a 90 degrees angle, so that the distance from here to there, this from here to there are the same. So that's not going to be exactly a 90-degree angle, but it's going to be really close, especially if L is a big distance. Okay, so then what we got is we've got a small triangle. And so this extra distance that the lower light ray had to travel, that the upper light ray did not, if it's going to a place that's bright, then that extra path difference is equal to lambda. Now, if it's going to the second diffracted bright spot, then it would be 2 lambda. If it's going to the third diffracted bright spot, then it would be 3 lambda. But we're interested in just the first bright spot. So that's going to be lambda. And then this distance right here, we call that D. And then I said without proving that the red angle right here, this angle theta right there, and then the black angle theta right here are equal to each other. I said that without proving it. I hope that what you did was you went home and drew some pictures and looked at it and convinced yourself that, yeah, that makes sense. So because the red triangle and the black triangle are similar triangles, that means if we take the ratio of any corresponding sides, they have to be the same. So if we take the ratio of lambda over D, okay, so it's that side over that side, the corresponding side on the black triangle would be X over H. Oops, sorry, try that again. Okay, X over H. Okay, so this is rigorously correct. Okay, this is rigorous. Oh, I'm not having, I'm trying to spell the word rigorous, but I don't have enough room there. Okay, but if L is much, much bigger than X, then L is approximately equal to H. So what we can do is we can take this equation here, the rigorously correct one, and we can say, well, that's approximately equal to X over L. And so then in last night's homework, what we did was we just said, okay, so this then is approximately equal to that. And so that made the homework a lot easier. Let me warn you, when you take the quiz, I've purposely put some problems in there where the small angle approximation in one case works pretty well, but in another case, not so well. So be careful about when you use the small angle approximation. When you take the quiz, it'll be obvious to you. Okay. So do not assume that the book, because in the book, they make it sound almost as if you could use the small angle approximation all the time. And that is not the case. You can only make the small angle approximation if L is much, much bigger than X. And that is not always going to be the case. Okay. With that, let's go ahead and move on to the new stuff. So let's see. Let me share a screen with you. So we are going to continue on in chapter 19 today. We're only going to do the middle part of chapter 19. Now, I do not intend to do all of chapter 19. The stuff that we do today will be the only stuff that we're going to do in 19. After we finish today's stuff, we're going to jump back and we're going to go back and pick up some things in chapters 16 and 17 that we missed. I like to do things in a slightly different order than the book does. So that's why I do 19 first before 16. But there's some really good stuff in the last half of the chapter that I wish we had time to talk about because it's really great, interesting, and useful stuff. But there's just not enough time in the year to do all the cool stuff. So unfortunately, we can't. Right. So what we're going to do tonight is we're going to deal with something called thin film interference, which is something that you have all seen. You just may not have known that you were seeing it. So what I'm going to do here, let's go back to here. And let's take a look at tonight's homework because I posted another video on the page that has tonight's homework on it that is really useful. Okay, so here's tonight's homework. And so, well, actually, tell you what, before we do this, let me do something else first. In order to do tonight's homework, there's one thing from the previous chapters that we skipped over that if you don't know it, you're not going to be able to do tonight's homework. So let me just go back and really briefly talk about this one thing, which is really important and I think really easy to understand. Let's suppose that you're in a spaceship and you're looking out the window. So I'm going to draw a cross section of the window. So here's glass. Here's you on the inside. So it's a very big picture window here. And so you are breathing air. On the other side of the glass is vacuum. It's the vacuum of empty space, which as I said a few minutes ago is not really empty. But in terms of whether there's molecules there or not, there are no molecules there. So it is a vacuum. That much is absolutely true. All right, so the speed of light is really interesting. You need to know a few things about that. Measuring the speed of light was a really big achievement because back at Isaac Newton's time, everybody assumed that light just traveled instantly. I mean, you turn on a light and instantly it travels to everywhere. But in fact, light does have a finite speed. And next time that we meet, we're going to talk a little bit about how they measured it because it was very clever and some really good physics involved in it. But for right now, let's just take it for granted that people have measured the speed of light and it is a finite number. And it's such an important number that they've even given it its own special letter. And that letter is C. Okay. And so that number is 2.998 and a bunch of other stuff times 10 to the 8th meters per second. Now, if you're only needing 3 sig figs, you can round that off to 3.00 times 10 to the 8th. Okay, so this is the number that we're going to be using most of the time because most of the time we don't need more than 3 sig figs. But recognize that the real true number is not exactly 3. It's actually a little bit less than 3. Okay, so you've got some light coming along and it's traveling here and it hits the glass. And hopefully you guys remember that whenever a wave encounters a medium, whenever it encounters a boundary, so that it's traveling from one medium into another medium, two things happen. So one thing is that some of the wave is transmitted, but also some of the wave is reflected. All right. Now, the percentage that's transmitted and percentage that's reflected, it depends on a whole lot of things that I'm not going to go into either now or ever during this class. This is beyond the scope of a high school class. That's more of a college class. But some is transmitted, some is reflected. Okay, now the transmitted wave is now in a new medium. Glass is the medium that it's traveling in. And when a wave enters a new medium, hopefully you guys remember, what is it that determines the speed of the wave? Answer, the properties of the medium. So it should come as no surprise that the velocity of the light inside the glass is going to be different. And it turns out that it's always slower. The fastest that light can ever travel is if it's in a vacuum. And if it goes into any non-vacuum medium at all, it's always going to be slower. So the velocity out here is 3 times 10 to the 8th, actually 2.997, but we'll just call it 3. The velocity inside here is less than 3 times 10 to the 8th, right? And so what we could do is we could just, write down what the number is, but it turns out that there's an easier way, more convenient way to deal with it. What we're going to do is we're going to introduce a new concept called refractive index. And we're going to give it the letter N, and we're going to define it to be the speed of the wave in the medium I'm sorry, I got that backwards. Try that again. It's the speed of light in vacuum divided by the speed of light in the medium. Okay, so this is in vacuum, and this is in whatever medium it is that you're interested in. And both of these are the speed of light. Okay, so because the speed of light in a non-vacuum medium is always less than the speed of light in vacuum, that means that N is always going to be a number that's greater than 1. And so like for instance, one of the problems that you're going to see in your homework tonight might be like this. They might be that I want to know what is the speed of light in glass. So what I'd need to know is I'd need to know what is the refractive index of that glass. And now there are different types of glasses, but common window glass usually has a refractive index of about 1.5. Now different types of glasses might be as high as 1.6, might be as low as 1.4, but let's just go with 1.5. Okay, so we've got vacuum out here. And so along comes a light wave that's traveling at the speed of light, which is 3 times 10 to the 8th. So my question in the homework then would be, what is the speed of light in the glass? Okay, so Sam, I see your question, and it is an important question, but let's answer this one first, and then remind me if I forget. We'll come back and get your question later. Okay, so I want you guys to do the calculations, and then in the chat box, I want you to send me a private message. I want it to be private so that other people can't see it. I want you to tell me, what is the speed of light in glass if the refractive index of that glass is 1.5? So please type it in the chat box. Okay, I'm not seeing any answers yet. Okay, now I'm starting to see some. Okay, so you guys are using the definition of refractive index, and you know what number C is, and you know what N is, so this should be trivial. Ah, okay, good. It does appear to be trivial. It looks like everybody's getting the same answer here. That's good, because when I did this with the A3 period earlier this morning, about half the class got this wrong. But looks like you guys are doing it good. But I'm not seeing answers from everybody here. What about the rest of you? Are you guys awake? Do you want me to start naming names here to embarrass you? I want everybody to respond, so I don't have to name any names. Yes, Sam, I'm not picking on you intentionally, but it does seem that you're the one that gets picked on more often than not. Okay, so all right, so for the sake of those who didn't put in answers here, let's just do it together really quick. Okay, so we know that n equals c over v. So all we have to do is solve that for v. So if we swap places with n and v, what we'll get is v equals c over n, which is 3 times 10 to the 8th divided by 1.5. And when we do that, we get 2 times 10 to the 8th. And the units are going to be meters per second. Okay, very good. All right. So now let me ask, what's going to happen to the light when it comes out the other side of the glass? So remember, when we set this up originally, we said that it was vacuum on the outside because this is a spaceship window, right? So on the outside is vacuum, and then here's the glass, and on the inside is air. And so now I want to know, what is the speed in air? Well, before we could answer that, we'd need to know what the refractive index of air is. And it turns out the refractive index of air is a number that's so close to 1 that it might as well be 1. The number is like 1.0000, and there might even be a couple more zeros. I don't remember exactly, but then eventually we get to a digit that's not 0. So if we're going to cut it off at 3 sig figs, well, look at that. The refractive index of air is a number that's so close to 1 that it might as well be 1, which means that the speed of light in air is a number that's so close to 3 times 10 to the 8th that it might as well be 3 times 10 to the 8th. Okay, so the speed of light in air is 3.00 times 10 to the 8th. Now, if we need more sig figs than that, then we have to account for the fact, that air does not actually have a refractive index of 1. Okay, now here's the interesting thing. This is explainable only if light is a wave. If light was a particle, this would not make sense. Think about it. Here is the window, so here's the glass. If light was a particle, so here it is, so think of it like a little bullet or something that's traveling through the vacuum here. So this is a vacuum, right? So it's coming along at a really high speed, 3.0 times 10 to the 8th, okay? And then it goes in the glass. And so because of the glass, it slows down. So it slows down to 2 times 10 to the 8th meters per second. Now, when this little bullet comes out the other side, it's not going to speed up again. I mean, once the bullet has been slowed down, it's going to stay at that slower speed. But what we've observed is that it doesn't. It speeds back up again. And it goes back to being 3.0 times 10 to the 8th again, which it could not do if it was a particle. Only the wave theory of light explains this, because the thing that determines the speed of a wave is the properties of the medium. So if it goes from a medium where n is 1.5, which is kind of, think of it like a thick medium, and it moves into a medium where n is 1.0, it's going to speed up. Okay, so it does make sense. All right, so that's something you might see in the homework there. All right, now Sam was asking about, what about tinted glass? Well, tinted glass just means that the glass is going to partially absorb some of the light. So if you get a really bright light hitting on the outside, the light that comes through and makes it out the other side is going to be a lot less intense, but the speeds will be exactly the same. Okay. All right, now, somebody did just send me a private message that says, but wait a minute, light is both a particle and a wave. Well, that's not really true. It is a wave. It is always a wave. It is completely a wave. It's just not the kind of wave that people think about when when they hear the word wave. Now, this is not something that I wanted to go into in any depth today, but I should mention really quickly. When people think of the word wave, they think of something like this. That's not what a light wave looks like. A light wave looks like this. Okay, it's a little bundle. It's a little wave packet. It's not something that goes on for an ever and ever. It's just a short little burst of a wave. Now, I don't want to go into any more details right at this moment. I will go into a lot more details later because this is something that's super important. But this is the famous photon that you've heard so much about. It is not a particle. It is a wave bundle, which you could say is, because it's a little finite packet, a little finite bundle, you could say that it has particle-like properties, but it is not a particle. It is a wave. It's just not a classical wave. It's a quantized wave. So we're going to go into that in great detail later. I don't want to go into it now. Okay, so now that we understand that, okay, let's now go and let's take a look at this video that I was going to show you earlier. Okay, what you're seeing here is a ring that has a soap bubble in it. I mean, you guys have all played with soap bubbles when you were kids, right? You take that wand, that little plastic wand that's got a handle and it's got a little circle on it, and you dip it in the soapy water and then you pull it out. And so what you're seeing here is the wand when it has just barely been pulled out of the soapy water, but it's got these funny colors, which hopefully you noticed. I mean, when you were a kid playing with soap bubbles, I hope you noticed that the soap bubbles had these really beautiful rainbow colors on them. Okay, well, we're going to find out today why. In fact, that's the whole focus of tonight's homework, is why does it have these colors? So I'm going to start the thing going. Now, what you're looking at right now is the dish. It's a thin, it's like a Petri dish in your biology class. It's a very thin dish, and it's got some soapy water in it. And there's a really big bubble sticking off the top here. So look at all the beautiful patterns and the colors. Okay, so the wand was inside the dish and it's just been lifted out. Okay, all right, so what you're seeing, so the round thing is the part of the wand that was stuck in the soapy water. And so there is now soapy water inside this wand. There's soapy water all inside of here. Now it's been turned vertically, and then it's stuck on this holder here. And the reason that the water doesn't immediately all rush out is because the soap has a very high surface tension, and so the soap is able to maintain the water in the hoop there. All right. So let's watch what happens as time goes on. I'm gonna start playing the movie again. Oh, and also one other thing that's really important I should tell you is that the camera is in front of the hoop looking at it. Behind the camera, there's a white light. And so imagine that you're standing here looking at it, there's a white light behind you. So the white light is coming behind you, it's hitting the soapy water, and then it's reflecting back to you. So all of the colors, all of the colors that you see here, that's the reflected light that's coming back from the white light that's behind us. Okay, so now let's start this video going again. I want you to watch what happens as time goes on. It's really interesting. Okay, so you see the color bands, and as time goes on, they move. The color bands that are up at the top here, they are wide. The color bands that are down at the bottom, they are narrow. But also notice, as time goes on, the colors that you see are vivid. Okay, that's a nice bright orange or nice bright yellow that you're seeing there. That's a beautiful deep orange that you're seeing there. As they get down here, the colors get all muddy. I mean, they're still there. I mean, you can see this kind of a reddish and kind of a greenish and kind of a bluish, but it's not a beautiful, clean red or a beautiful, clean blue. It's muddy. Whereas up at the top, you get all these beautiful, vivid colors. Turns out that's really, really important. Do you notice what's happening up at the very, very top? It's just black. It's totally black up there. No colors, no nothing. Ooh, that's interesting. Why do you suppose that is happening? Tell you what, I'm going to stop the video. Can anybody suggest a reason why it is that we're seeing total blackness up at the very, very top? Anybody want to give it a shot? All right. Okay, so one person just sent me a private message, so I won't say their name. And the person said, well, maybe that's because there's no soapy water there. Maybe the soapy water only extends up to a certain point here. So let me clear out everything here. Okay. So this one person said maybe the soapy water only goes up to here. Okay. And then this part right here is just air. Okay. Well, that would make sense, except those of you who've played with soap bubbles, you know that when you have a soap bubble, if you poke it, if you put even a tiny little hole in that bubble, the entire bubble instantly collapses, right? So if it's true that there was a break in the bubble right here, if that was the case, this entire bubble would instantly collapse. So up at the top there, it turns out that it is not air up at the top. Okay, that's not the reason. There's a very different reason, and it's a reason that we're going to talk about right now. So let's see. Connor says that the parts with the color are denser, so they fall faster. Okay, you're on the right track there, Connor. But let me open up a whiteboard in order to explain what's happening here. Okay, so what I'm going to do is I'm going to draw the soap bubble, and the first time I draw it, so here's the wand, here's the hoop, and then the soap. Okay, can't spell soap here, can I? Okay. So the soapy water completely fills the hoop. So this is the front view. Okay, but I'm more interested in the side view. Okay, so what's happening is we've got a light bulb right here, and then the light is shining over here. Now, if we look at the wand from the side, so here's the upper part of the wand, here's the lower part of the wand, and in between here, this is the soapy water. Okay, so the light is coming here, it's hitting the surface, and it's reflecting back. So we are looking at the reflected light. Okay, but let me zoom in a little bit here. Let me draw the picture a little bit closer up. So what's actually happening in a greatly exaggerated form is this. Okay, notice at the top of the column here, the film is very thin. And down at the bottom here, it's thick. And so what's happening is on the outside surface here, that's where the soap is, and it has a really high surface tension. So it's able to maintain a film. And then, so on either side, on the inside and the outside, we have the soapy film. And then inside, that's where we have the water. Okay. And gravity is acting on the water. Gravity is trying to pull the water down. Now the soapy film on the left and right edges, that's trying to hold on to the water and is trying to prevent the water from going down. But as time goes on, the water is going to get more and more down. And so at some point here, now this is terribly, terribly exaggerated, but at some point here, the bottom is going to get super thick. But the top, even though the top gets super thin, it's not going to go to zero. There is still soapy film there. All right, so let me draw the picture one more time here. Okay, so here is super thin, and here it's thick. Here comes the light, and so this is the light that's coming in, and it hits the surface. And remember what we said, whenever light hits the surface, some of the light is reflected and some of it's transmitted. So tell you what, I want to make this even fatter. Let's make it be super fat. So this is the water, this is the air, and we have more air here. Okay, so the light is coming in, and whenever a wave encounters a boundary, some of the light is transmitted, some of the light is reflected. Okay, so this transmitted light, it's going to travel through, and when it comes to the other side of the film, it now encounters another boundary. And so what's going to happen is that some of the light is going to be transmitted and some of the light is going to be reflected, just like before. Now, let's look at the reflected ray here. So the reflected ray comes out here. When the reflected ray gets to this boundary, well, again, some of it's going to be reflected in here and some of it's going to be transmitted. And when it comes down to here, some of it's going to be transmitted and some of it's going to be reflected. So we get all these really interesting bouncing around going on. But each time it encounters a boundary, the intensity, it becomes less and less. So we start off with 100% intensity, and then in here, maybe we've got 90%, 10%. Now I'm just making up numbers here. And when we come here, we're down to about 91, we're down here to about 81% and 9% and about 9% there. So, I mean, every time we bounce here, we lose intensity. So we can pretty much ignore all of these others. The only ones that I care about are these two rays right here. So let me make them fat. So this ray right here, I'm going to call this R1. This is the ray that got reflected off of the front surface. This ray right here, we can call this R2. This is the ray that had to travel all the way through the film, bounce off the other side, travel back. So if we look at the change in the path length, so I'm going to say delta path length. Okay, so that's the distance that the R2 had to travel that R1 did not. You guys see that that's not going to be the same as the thickness of the film, because we went through the film and back. So the path length difference there is going to be twice the thickness of the film. Okay, you guys agreed with that? Okay, so delta path length stands for the distance that ray 2 had to travel that ray 1 did not. So it traveled a greater distance, and that distance is not equal to the film thickness, it's equal to twice the film thickness. Okay, now here comes the good part. When these two rays come out here, they are actually going to lie on top of each other. They are going to combine together, and they are going to interfere with each other. So they might interfere constructively, they might interfere destructively. So here's ray 1. Let's say here's ray 1, it looks like this. Okay. And ray 2 is the same wave, but it traveled a greater distance than ray 1 did. So I'm going to put it in a different color, even though this is actually the same color light, because the wavelength of the light is, that's what determines what color it is. So I'm going to draw it as a different color, not because it actually is, but just to keep them straight. So R2, I'm going to do in blue. So R2 wave looks the same as the R1 wave, but it's going to be shifted over a bit because it had to travel a greater distance than the R1 did. This is very much like the double slit experiment. Remember when with the double slit experiment, we said that the one ray had to travel a greater distance than the other ray did? And so when they get to the wall, if they combine together in a constructive way, you see brightness. If they combine together in a destructive way, you see darkness. So if this distance right here, this is delta path length. Okay. Then if I was telling you the complete story, which by the way, there's one thing that I'm purposely leaving out. I'll tell it to you in just a minute. But if I was telling you the complete story, then if delta path length was equal to lambda, so then what that means is that the second wave, instead of starting here, it would start here. So you can see then we would have constructive interference. If, on the other hand, delta path length was equal to lambda over 2, okay, so that means that that starts off right here. So let me get rid of this guy. So if that was the case, it would start off right here. And so you can see that the peak of the one wave lines up with the trough of the other wave. So that would be destructive interference, okay? And so we could tell whether these light rays are going to interfere constructively or destructively. You know, if I was telling you the complete story, which I purposely am not, but don't worry, I will tell you the complete story in just a minute. But if that was all we had to worry about, then we would know whether or not these two light rays are going to interfere constructively or destructively, okay? We would just look to see. We would say if the change in path length, which is 2t, if that was equal to lambda, then they would interfere constructively. And so that means we would see brightness. If, on the other hand, 2t was equal to lambda divided by 2, then that would correspond to destructive interference. So what we would see would be darkness. So you see this effect that we're talking about right now, which is called thin film interference, is not really that different from the double slit experiment, okay? Now, I've said many times here, if I was telling you the complete story, then we're done and you could get to work on tonight's homework. But there's two important things that I've left out. And so now we need to go back in and we need to pick up those two important things that I left out. And let me go to a brand new page here. I want to start with a nice clean drawing. So here is the surface. So here is the water, and here's the air, and here's the air. And so now here comes the light ray. Okay, so ray number 1 is that one. Ray, and the thickness here is that. So ray number 2 goes through the water film, comes back, and it comes out here. So here's ray number 2. What about phase change that happens on reflection? We ignored that. If you ignore that, you're going to get the wrong answer. You need to worry about it. Remember on the test, one of the questions on the test last week was asking you about if a wave is coming from one medium and it travels into another medium, is the reflected pulse inverted or is it not? And that was a question that many of you got wrong. So we better take a minute, we better talk about that, because now is when this becomes critically important. So if you have a string, and here's a pulse in a string, and then here is a heavy rope. So what we have on the left here is a light string. On the right, we have a heavy rope. Okay, and so the pulse is coming in along here. And when the pulse gets to this point right here, so it now has hit the wave boundary. So some of the energy is going to go in here and we're going to have a transmitted pulse, but some of it's going to be reflected. Okay, so if this is the before picture up here, and down here is the after picture, there's two possibilities. One possibility is that you've got a transmitted pulse traveling right here in the heavy rope. And by the way, the transmitted pulse, the phase of the transmitted pulse is never inverted, never ever. But the reflected pulse, maybe it is, maybe it's not. Okay, so it might be that the reflected pulse ends up looking like that, or it might be that the reflected pulse ends up looking like this. In both cases, the reflected pulse is now traveling to the left, but it could be inverted or it could be not inverted. Okay, so let me ask you a question like I asked on the test, and let's see if you can do it better this time than you did last time. So if we're going from a light string into a heavy rope, is the reflected pulse going to be inverted or not? I want you guys to type in the chat box in a private message so nobody else can see. I want you to type in either inverted or not inverted if you're going from a light string to a heavy rope. Now, if you need a hint, I can tell you that the speed of the wave is going to be faster in the light string than it will be in the heavy rope. And no, this is not a trick question, okay? Which is an answer to a question that somebody just asked me privately. This is not a trick question. It's either going to be inverted or it's going to be not. So it looks like most of you have an opinion. Yeah, so far, everybody has said it's going to be inverted. Okay, good, because everybody is right. That is, in fact, what's going to happen. So let me erase this guy. Okay, so if you're going from a light string to a heavy rope, it will, in fact, be inverted. And so I'm glad to see that you guys remember it. What if it's going the other way around? What if you start off in a heavy rope, okay? And so you're coming along this way. So this is the before picture. And then the after picture. Okay, so here is the transmitted pulse, which hopefully you guys remember, the transmitted pulse is never inverted. But the reflected pulse, what's it going to be in this case? Again, type it into a chat box. Is the reflected pulse going to be inverted or is it not going to be inverted? Okay, all right, good. So you guys are correct in saying that the reflected pulse in this case will not be inverted. Okay, all right, great. So they called? Okay, okay, okay. Oh, do I need to talk to him? Okay, excuse me, guys, I got an important call. Let me just put you on hold for just a second. Okay, I'm back. I apologize for that. Yeah, as Sam is saying that I got called to the principal's office. Actually, it was somebody even with more power than the principal. It was my wife. Okay. All right. So I see that you guys have not typed into the chat box here. But the correct answer here is that it will not be inverted. Okay. So now what we need to do is we need to go back here and we need to make a few adjustments to what I told you a couple minutes ago, because one of these light rays is going to be inverted. So the question then is which one? So if we're coming from air, where the speed of light is 3 times 10 to the 8th, and we're coming into water, where the speed of light is 2 times 10 to the 8th, or something similar. Actually, it's not exactly 2, but it's less than 3, okay? So the velocity is less than 3 times 10 to the 8th, because the refractive index of water is not 1.5, it's something else. It's actually 1.3. Okay, so if you're going from air into water, that's like going from a light string to a heavy rope. So R1 here is inverted. So that changes everything. Everything that I told you back here about where I said that if the path length is equal to lambda, then you get constructive. Well, that's not going to be true anymore because R1 got inverted. So that throws a wrinkle in everything, but it's a wrinkle that we can deal with. Okay. So what I'm going to do is I'm going to redraw R1, and I'm going, instead of drawing it the way that I did here, let me draw it upside down, and let me make it fat. So R1 is actually going to look like this. Oops. Okay. All right, so ignore that. All right, so let me erase the old R1, so I've got the new one. So now, how does that affect the rules? Well, what about R2? Before we talk about the rules, let's decide, what about R2? Does R2 get inverted? Because if R2 also gets inverted, that's important to know, right? So what we need to do is we need to say, okay, well, let's look at R2. So where did the reflection occur for R2? It occurred right here. What happened was R2 was coming from water going into air. So some of the light was transmitted, some of it was reflected. So if you're going from water, where the speed of light is slow, into air, where the speed of light is high, well, that's like going from a heavy rope to a light string. So the reflected pulse here is not inverted. But so R1 is inverted, R2 is not inverted. Okay, so now let's go back to here. So the black line that you see, that is the inverted R1. The blue line that you see, that is the non-inverted R2. And let's start with a nice clean drawing here. Okay, so here is the start point right here. Let me do this in black. Okay, so normally I would draw R1 as being like this, but R1 got inverted. So I'm going to draw it like this instead. Now R2 did not get inverted. So if the change in path length was 0, if the thickness of the film was 0, so that R2 really didn't get shifted by any appreciable amount. But remember, R2 is not inverted. So what we're going to get is going to look like that. So in blue, we're seeing R2, and in black, we're seeing R1. And so if the change in path length is 0, so in other words, if the film thickness is equal to 0, then you can see that what we're going to get is destructive interference. Okay, does that make sense? If the film thickness was so thin that we could call it 0, even though, I mean, it's never going to be 0, but if it's so thin that it's indistinguishable from 0, then because R1 is inverted and R2 is not inverted, when those two light rays combine, they are going to combine so that the peak of the one wave corresponds with the trough of the other wave. And what you're going to get is destructive interference. They're going to cancel each other out. And that is exactly what we did see. If we go back in here and we look at the film, what do you see up at the very top? You see darkness. And the reason we're seeing darkness is because we're getting destructive interference at that point. So the film up there is so thin that for all intents and purposes, the thickness up there is so close to 0 that it might as well be 0. And because one of the light rays is inverted and the other light ray is not, they interfere destructively, and so you don't see any reflected light from there. Okay, does that make sense? All right, now Why do we see all of these beautiful colors? What's going on there? Well, let me open up a whiteboard. Okay, so let's draw R1. So here's R1, which normally I would draw like that, but remember it got inverted. So I'm going to draw like that. Okay. And now R2 has been shifted by a certain amount, because now we're going to say that the thickness is not equal to 0 anymore. The thickness is now some non-zero value. So what that means is when I draw R2, I'm going to have to draw it as being shifted by some amount. If that shift amount is exactly equal to lambda over 2. So if the change in the path length is equal to lambda over 2, look what happens. The peak of R2 corresponds with the peak of R1. And the trough of R2 corresponds with the trough of R1. So what have we got? We've got constructive interference. All right. Okay, so we've got constructive interference. So that is only going to occur if the shift in the path length is exactly equal to lambda over 2. And remember that the shift in the path length is equal to 2t, except, I hate to say this again, but there's one other little detail that I'm leaving out right now, but I'll come back in about 2 minutes and I'll fill you in on this one remaining detail. But for conceptually, you can see that if twice the film thickness is exactly equal to lambda over 2, then we will get constructive interference. Okay. And if twice the film thickness is equal to 0, then we will get destructive interference. Okay. Now, what are the other times? What if twice the film thickness equals lambda? What are we going to get then? Going to get constructive or destructive? Well, I don't want to take the time to go into it right now because we're running short on time. So if twice the film thickness is equal to 0 or lambda or 2 lambda or 3 lambda or any multiple of lambda, then you will get destructive interference. If, on the other hand, twice the film thickness is equal to lambda over 2, or if it's equal to 3 lambda over 2, or if it's equal to 5 lambda over 2, okay, then you will get constructive interference. Okay. So what we're going to do is let's make a rule that we're going to say if delta path length, which is equal, let me just get rid of that. Say if 2t equals 0 or lambda or 2 lambda, then you get destructive, which means that you will see darkness. If, on the other hand, 2t is equal to lambda over 2, or if it's equal to 3 lambda over 2, or if it's equal to 5 lambda over 2, then you will get constructive. But notice it will only get constructive for one of the wavelengths. Now, when I say one of the wavelengths, what I mean is this. Let's suppose I ask you a question. Let's say, what is the wavelength of red light? Well, some of you might know, red light has a wavelength of about 650 nanometers, plus or minus a little bit. Blue wavelength has a wavelength of about maybe 450 nanometers, plus or minus a little bit. You know, green has a wavelength of about maybe 520, you know, plus or minus a little bit. Okay. What about white? What is the wavelength of white light? Anybody know? Anybody want to unmute themselves and tell us? Well, tell you what, we're running low on time. Let me tell you, that's a trick question, because white light is actually a combination of all of these others. If you take red, blue, green, mix them together, that is white light. So white light doesn't really have any one particular wavelength. White light is a mixture of all of the wavelengths. Okay, so what's going to happen then is if I shine white light on a film, so this is air, this is water, and this is air. So I get R1 comes reflected there, R2 comes reflected there. So if 2t is equal to lambda over 2, then we will get constructive interference, but only for one of the wavelengths, because white light is actually a combination of many different wavelengths. So this magic condition here where 2t equals lambda over 2 will only be true, so you'll only get constructive interference for one wavelength. And so that means when you look at the reflected light, you will only see one color. And the color you see depends on the thickness. So for some thicknesses, red is the color that you'll see because it'll be constructive, everything will be destructive. For other film, for when you go down just a little bit where it's a little bit thicker, then you're going to see green. Go down a little bit more, you're going to see blue. Okay, now we're almost out of time. There's one super important thing that I did not tell you because I didn't want to complicate things too much. Lambda has to be the wavelength in the water, not the wavelength in air. So if we're talking about green light, okay, so when we say the green light has a wavelength of 520 nanometers, well, that's what the wavelength is in air. When that green light, so here's air, here's water, here's air again. So here comes the green light, and the wavelength here is 520 nanometers. When that wavelength goes into the water, that wavelength becomes shorter. So it's not 520 anymore. It's now a different number. And it turns out it's an easy number to get. When it's in the wavelength becomes what the original wavelength from air would have been divided by n. Okay, so all we have to do is go back to here and replace lambda with lambda over n. So we get an n right here. So there, now we have the full complete thing. And I have now told you everything that you need to know. I'm not hiding anything else. So let's summarize this one more time. So if 2 times the thickness is equal to lambda over n, well, actually, let me rephrase that. If it's equal to 0, or if it's equal to lambda over n, or if it's equal to 2 lambda over n, or if it's equal to 3 lambda over n, then you will get destructive interference. If, on the other hand, twice the thickness is equal to lambda over 2n, or if it's equal to, let's see, 3 lambda over 2n, or if it's equal to 5 lambda over 2n, okay, then you will get constructive interference. Okay. All right. So we got to go now. The bell has rung. Look on Canvas to find out what the homework is. And I think it's pretty straightforward. Okay. Any last minute questions? All right. Head off to your next class, guys. I'll see y'all later.